Hello and welcome to the screencast for AlloyFL, a fault localization tool for Alloy. First, before presenting the tool, we have a website designed to consolidate information for the user. The top portion contains relevant information for successfully downloading and executing AlloyFL. Tool is a link to a precompiled jar file the user can download and execute. We also present a link to a GitHub repository that has our source code, which enables users to download and build AlloyFL themselves. The repository also contains our models used to evaluate AlloyFL, which can serve as example usage for new users. Next, we present the requirements needed to execute AlloyFL, including the supported operating system and version of Java. And lastly, we include a link to a paper which covers the technical content which defines fault localization for Alloy models and presents the hybrid fault localization technique that AlloyFL is an open source implementation of. On the bottom, we have a link to 3 pieces of software which are integrated into AlloyFL. The analyzer, which is the main IDE for Alloy, the A-unit analyzer, which allows users to declare and execute A-unit test cases, and MuAlloy, which introduces mutation testing for Alloy and is incorporated as part of the fault localization strategy. Moving on to the tool itself, depicted on the screen is AlloyFL's GUI interface. AlloyFL is an extension of the A-unit analyzer, which is itself an extension of the Alloy analyzer. This means that users are able to directly edit and build Alloy models following all of their standard development practices that they're already used to. However, whenever they encounter a faulty A-unit test case, they now have the ability to perform fault localization using AlloyFL. So this is an extension on top of the A-unit analyzer, allowing us to make use of native support for A-unit test cases. To highlight how all of this comes together, we're going to step over a faulty model of a singly linked list. So we first declare list as a named set of atoms, and we introduce through the header relation the idea that each list is either empty or it points to exactly one header node. Similarly, we introduce node as a named set of atoms, and we say that each node atom then has a link that is either empty or points to exactly one other node. Then, by outlining this predicate acyclic, we are attempting to express the idea that we want to prevent cycles from appearing in our list. To achieve this, we use this universally quantified formula that says for all nodes n, if n is in the list, then n is not reachable from itself. The fault in this model is subtle, and it lies in this single character here, the asterisk, which in Alloy represents reflexive transitive closure. Unfortunately, the use of reflexive transitive closure includes the original n node itself, which means that every node is always going to be reachable or viewed as reachable from itself no matter what. To correct this model, we can swap reflexive transitive closure for transitive closure, which is the difference of a single character. But for now, we will keep the fault in place in order to perform fault localization. So besides having a faulty Alloy model, we also need a fault revealing test suite. Depicted here is an automatically generated test suite, which was generated by using mutation testing and generating tests that kill all non-equivalent mutants. To highlight a test, we have up top here one such test. Val allows us to indicate that we are declaring the valuation portion of an A-unit test case. From there, we step over the structure of a Alloy scenario that's outlining a single list with one header node, and then that node just points to another node in the list. We use @command to flag the command for our test case, and then @test on the bottom is the executing command for A-unit. If we run this A-unit test suite in its entirety, we can see that this fault revealing test suite actually fails across 7 tests and passes for 15. So those are the two elements we need in place to run fault localization: a faulty alloy model and a fault revealing test suite. From there, we can now perform fault localization. To help the user do that, we have a tutorial that they can view. We contain a brief motivation for why we wanted to add fault localization to Alloy. But more importantly for the user, we step over what it means to set up a fault localization problem by outlining the hybrid fault localization technique that AlloyFL implements, a reference to the suspiciousness formulas that they can select, and a high-level outline of the two techniques, coverage-based and mutation-based, which are combined together in the fault localization technique. We also contain a section that is a brief reference to what the different parameters the user can configure mean so that they can know what they're changing when they make their choices. To illustrate that, you can go to the drop-down menu to configure two different things for AlloyFL. The first is a weight applied between mutation-based fault localization and coverage-based fault localization. The weight is defaulted to 0.4. That comes from a larger study over real-world faults that found that 0.4 was the best on average weight between the two. What the 0.4 means is that for the mutation scores calculated under AlloyFL's hybrid technique, it will apply a weight of 40% to the mutation-based score and 60% to the coverage-based score. The other thing that the user can configure is the suspiciousness formula. We support 5 different suspiciousness formulas, and the default is selected to Okai, which was found to be the best on average, but all 5 can be selected from the user. Once the user is happy with their configuration, they can execute AlloyFL either through the drop-down menu or by selecting the AlloyFL icon. When that happens, the logging pane is updated to reflect where it is within the AlloyFL execution, so it reports back the parameters the user selected, as well as when it enters coverage-based and then mutation-based fault localization, and then whenever it is combining and reporting the scores. Once AlloyFL successfully executes, the user is presented with information in 2 ways. The model that they wrote on the left-hand side is highlighted with locations based off of their suspiciousness score. So red is going to indicate a highly suspicious location, whereas yellow would indicate a lightly suspicious location. On the right-hand panel, the AlloyFL results it sums up the total number of locations. It also presents the runtime to the user, which is then further broken down by the 2 different fault localization executions that get combined together. And then, importantly, we get our ranked list of suspicious locations presented in order from most suspicious to least suspicious. Within a given suspicious location, the user is presented with the expression or formula, the suspiciousness score, and then this highlight location feature, which will, if selected, the user then is viewed with just that location highlighted and the color coordinates to its given suspiciousness score. This is in particular valuable because if we look at this list of suspicious locations, we can see that we have this reflexive transitive closure applied to the link relation in 2 different places. And if we select this other highlight location, we can see that this is actually just referencing the earlier subformula that used that same set of alloy expressions. Another thing to note is that these highlighted locations are done such that if a formula is within another subformula, whatever is the dominant or higher suspiciousness score will be displayed. What that means is that, for instance, if we look at this currently highlighted expression, we can see that its suspiciousness score is 0.61. and it is highlighted a mid-orange color. But when we go to highlight all locations, it's overwritten by a red color because it's within a larger formula that was found to be more suspicious. Additionally, from this example, we can see that our faulty location is presented as the most suspicious location, and it is the deepest red colored location on the left-hand side. We can then look to, as mentioned earlier, correct this fault by switching it to transitive closure instead of reflexive transitive closure. And when we run our A-unit test suite, we now see that all tests pass. This was the screencast for AlloyFL, a fault localization tool for Alloy. Thank you for watching.